Hi, my name is Rachel. Welcome to this exciting journey into the world of blockchains. Today, we are going to study consensus mechanisms. These are the rules that allow thousands of computers around the world to agree on one shared truth, the blockchain. Let's dive in. What is consensus? Consensus means agreement among many participants. In the context of blockchains, it's how multiple computers, called nodes, agree on the next block to add. Without consensus, some nodes may record different histories, creating confusion. Consensus ensures everyone sees the same transactions as valid and secure. It is the backbone of trust in decentralized systems. Why consensus is important? Imagine if banks all kept different records of your balance. Chaos. Similarly, without consensus, blockchains wouldn't work. Consensus prevents double spending, ensures fairness, and keeps the system running without a central authority. It allows strangers across the world to coordinate without needing to trust each other. Proof of work, POW. Basics. Proof of work is the original blockchain consensus mechanism used by Bitcoin. Here, miners compete to solve tough math puzzles. The first to solve gets to add a new block and is rewarded with cryptocurrency. This puzzle solving requires huge computing power and electricity. POW ensures security but is criticized for being energy intensive. Proof of work in detail. Let's go deeper. Miners take pending transactions and pack them into a block. They then try to find a hash, a digital fingerprint, that meets a very strict condition. This can take trillions of guesses. Once a miner succeeds, the block is broadcast, and others verify it easily. This difficulty makes it nearly impossible for attackers to rewrite history. Proof of stake, POS, fundamentals. Proof of stake is a greener alternative to proof of work. Instead of solving puzzles, validators lock up some of their coins as a stake. The chance of being chosen to add the next block depends on how many coins they stake. Honest behavior is rewarded, while dishonest actions risk losing the stake. This uses less energy and allows faster block creation. Ethereum's shift to POS. Ethereum, the second largest blockchain, switched from POW to POS in 2022. In Ethereum POS, validators replace miners. Validators take turns proposing new blocks, and others vote to confirm. The system is organized into epochs, time periods, and slots, smaller units within epochs. This design makes Ethereum more scalable and eco-friendly. Validators, epochs, and slots. A validator is like a digital guard who maintains the blockchain. Validators propose blocks in slots, which occur every 12 seconds. Many slots form an epoch, about 6.4 minutes. Within an epoch, validators vote to agree on blocks and ensure consistency. This time-based structure makes the blockchain predictable and fair. Finality versus probabilistic settlement. Finality means a transaction can never be reversed. In POW blockchains like Bitcoin, settlement is probabilistic. The more blocks added after your transaction, the safer it is. In POS systems like Ethereum, finality is faster and stronger once validators confirm. This matters for things like payments, where irreversible records are crucial. Finality gives confidence that your transaction is set in stone. Leader, proposer. Selection. Who gets to propose the next block? In POW, it's whoever solves the puzzle first. In POS, it's randomly chosen from the pool of validators, weighted by stake. Some blockchains combine randomness and fairness to prevent manipulation. Leader selection is critical because it decides which transactions are added next. A good system balances fairness and efficiency. Validator rewards. Validators are motivated through rewards. In Ethereum, they earn fees and newly minted ETH for proposing and validating blocks. Rewards encourage honest behavior and continuous participation. If validators fail to act, they miss out on rewards. This economic incentive ensures the system keeps running smoothly. Slashing, punishing misbehavior. But what if validators cheat? That's where slashing comes in. If a validator tries to confirm two conflicting chains or breaks rules, part of their staked coins are destroyed. Slashing discourages attacks since cheating is expensive. Honest validators are safe, while dishonest ones pay the price. This is a powerful tool for blockchain security. BFT-style consensus. BFT stands for Byzantine fault tolerance, the idea that a system can handle some dishonest or faulty participants. Blockchains like Tendermint, used in Cosmos, and Hotstuff, used in Diem, use BFT-style consensus. Instead of relying on energy or stakes alone, they require 2/3 of validators to agree before finalizing blocks. This makes finality instant and very secure. However, BFT systems work best with smaller validator groups. DAGI-based protocols. Avalanche. Some blockchains use DAGs, directed acyclic graphs, instead of simple chains. Avalanche is a popular DAG-based protocol. In Avalanche, validators repeatedly gossip with random peers to check if a transaction is accepted. With enough rounds, consensus emerges very quickly. This makes Avalanche highly scalable with low fees. It's like polling the crowd until everyone agrees. DAG-based protocols. Hashgraph. Hashgraph is another DAG protocol, using a method called gossip about gossip. Validators share not only transactions, but also the history of who they talked to. This creates a shared record that everyone can trust. Hashgraph can achieve thousands of transactions per second. It's used in projects like Hedera Hashgraph. The focus here is fairness and high speed. Liveness versus safety trade-offs. Consensus mechanisms must balance liveness, the system keeps moving, and safety, no invalid blocks are confirmed. Sometimes prioritizing speed risks security. Other times, ensuring maximum safety slows things down. Bitcoin, for example, prioritizes safety by requiring confirmations. Some newer blockchains aim for both, but trade-offs always exist. Bitcoin's consensus model. Bitcoin uses proof of work with probabilistic settlement. It's extremely secure, but slow, with about 10-minute blocks. Energy usage is very high, but the system has proven robust for over a decade. Bitcoin sacrifices speed for maximum trustworthiness. This is why it's considered digital gold. Ethereum's consensus model. Ethereum now uses proof of stake with validators, epochs, and slashing. It's faster than Bitcoin, with blocks every 12 seconds. Finality occurs within a few minutes, offering quicker settlement. Ethereum also supports smart contracts, making it more versatile. This model balances decentralization, efficiency, and eco-friendliness. Other blockchain models. Different blockchains experiment with unique consensus methods. Solana uses proof of history plus POS for high throughput. Cosmos uses Tendermint BFT for fast finality. Algorand uses a lottery-style pure POS system. Each approach has pros and cons in terms of speed, security, and decentralization. The diversity shows how consensus keeps evolving. Conclusion. We've now explored the heart of blockchains, consensus mechanisms. From POW to POS, from validators to slashing, and from DAGs to BFT models, we've seen many ways blockchains achieve trust without central authority. Every design has trade-offs between speed, security, and decentralization. Understanding consensus is key to understanding blockchain architecture. Thank you for joining me on this journey.